Okay, so here we'll look at the case like series RLC circuit. So on the right hand side we have RLC in series. So you may consider we have seen this before, like the RLC. Yeah, something occurred before, like I mean here. Here we have RLC in series, but in this case, we don't have any source outside. So we only consider there are some initial energy stored in either L or C. Okay, so so we call it the natural response, or here should be the natural frequency. But here we consider we have a RLC circuit but in series with a sinusoidal source. So here the main difference is that this is a sinusoidal source, like an AC source. Sinusoidal source or AC source, because we talk about alternating somewhere here. Yeah. Alternating EMF, so which is actually AC, alternating current. Okay, so actually in the textbook it just tells you that, okay, when we have RLC in series, it is something like the impedance of R, L, and C in series. Yeah, actually they're in series. So if you haven't learned about the impedance, then previously when you have a resistor in series, then you can add the resistance together. When you have inductor in series, they are adding together. But for capacitor in series, they are not adding together. You need to take the reciprocal and then add them together, and then take the reciprocal again. But here, as much as we have ZZ to be 1 over J omega C, so it is just like we already take the reciprocal of the C. So we just need to add them together. In this sense, which means that when we consider the impedance in series, we just need to add them together. If you have impedance in parallel, you can just like Z1 parallel with Z2, and then it will become C1 Z2 over C1 plus C2, something like this. Okay, so you just need to follow one rule to calculate the RLC, but you need to consider the impedance, which makes impedance of L, impedance of C an imaginary number. So in this case, ZR is nothing but R, and then ZL is J omega L. So we have J omega L, and then ZZ is J omega 1 over J omega Z. So as I just explained previously, it is actually negative J over omega C. Negative J over omega C, which means if you just multiply J in the numerator and the denominator, so J squared is -1. Okay, so we have, this is the overall impedance of the RLC in series. Okay, so for the real part, it does not relate to the operating frequency. This omega D is the operating frequency of the source, which means that this E is something like EM cosine omega dt. Which means that we don't care about the natural frequency of the circuit. The natural frequency is still omega prime equals square root of omega square minus R over 2L square, something like this. So this omega is 1 over square root of LC, something like this. Here, this omega D can be arbitrary number, and different omega d will make the impedance here different. So you can see here, this is the impedance. So the imaginary part relates to this is related to omega d, So if just say if omega d is like 0, then you just plug in 0 there, then this is 0, this is infinity, okay? But if you just so this one becomes infinity, and of course the impedance is infinity, which means that current will be 0. Or the other way around, if omega d tends to infinity, okay, so this term tends to infinity, this is 0, okay, so this z also tends to infinity to make the current very small. But if omega d just close to this one, then we will have a large current there. Okay, so here is already mentioned. E is Em cosine omega dt. Okay, and it also tells you that tangent phi is the phase between the voltage and the current. Okay, so you can see I is the current, will be another sinusoidal. We only need to determine the amplitude and the phase, which is the phase between the voltage and also the current. And actually, okay, so you can see here, this is like this is V, this is you can see this is the actually this is the amplitude, this is the absolute value or the amplitude of the current here, and it will be like Em over the absolute value of C. So this is the absolute value. You can see here, this is a complex number. We need to calculate the absolute value. The absolute value of an complex number is like if we have alpha plus j beta. So this is an arbitrary complex number. The absolute value will be alpha squared plus beta squared, and then take the square root. So you have, this is the real part. This is the real part, r squared. So we have r squared here, and then this is the imaginary part. So we take the square of this part, which is here, and then add them together, take the square root, will be the absolute value of z. So this is actually absolute value of I equals Em over absolute value of z. And then we need to also determine the phase. The phase here is like, it's like if we have I equals E over Z. So this Z is like R plus J omega dl minus 1 over omega dz. Okay, so you can see this is a complex number, this is another complex number, but this is actually a real number, which means that the imaginary number is the imaginary part is 0. So it is like exponential to j 0. And for this imaginary number, complex number, I mean, so this is like and complex number can be written as the absolute value and then times exponential to j and then phi. This phi is actually like if you have a point on the complex plane, this is real part, this is imaginary part, and suppose this one is alpha plus j beta, and then we need to determine this phi. So this phi, you can have a tangent of phi will be beta over alpha. So in this case, this part, don't consider it as a denominator yet. Only this part will be like tangent phi. Tangent phi will be the imaginary part over the real part. so which is actually this one. And of course it is in the denominator, so which means that we altogether have I equals e exponential to j0 and then over absolute value of c and then exponential to j phi. So it turns out to be e over absolute value of c exponential to negative j phi. That's why we have a negative sign here rather than a positive sign. Okay, so actually we can actually deduce this one using the potential method, which means that suppose this one is em cosine omega dt, okay, and then we have r I z r l. Okay, so in this case we have em. Actually, writing the KVL, we have em cosine omega dt equals this one, r times I, and then for this one is VC, this one is VC. For VC, we have dVc dt, c times dVc dt is I, and then we have this one. This is VL. VL will have another VL equals L di dt. Okay, plus VL. Okay, so actually we can have Ri plus Vc plus L di dt. Okay, so we would like to construct this one to be this one, so we can take derivative on both sides. Take derivative on both sides. Em cosine omega dt. Okay, so we can take derivative on both sides. Then we can construct this dVc dt and then multiply by c, and then multiply by c. So we will have this one. Take the derivative will be omega d em and then times c, and then cosine become negative sine omega dt. Okay, so this omega d is due to the chain rule. So we have em here and then multiply by c here, and then the chain rule here. Cosine become negative sine, and then here Ri take the derivative will be R di dt, and then we multiply by c, so we have Rc di dt. And then next we have this one, take the derivative, c dVc dt. So finally it turns out to be I, and then plus this one, L second derivative of I, and then multiply by c. Okay, so here replacing this one by I, we have Lc d2I dt2 plus Rc di dt plus I equals negative omega d emc sine omega dt. And then we can just divide Lc on both sides, so that we normalize the leading coefficient of the linear constant coefficient ODE. So we have something like this, plus 1 over LCI equals negative omega d em, and then c and c will cancel, so we have L in the denominator only. So we have a constant coefficient ODE like this. So in that case, this is the homogeneous equation, d2I dt2 plus di dt plus 1 over LCI equals 0. So this is actually the homogeneous equation. Actually, for this case, we don't consider the we don't consider the homogeneous solution or the complementary solution, because IC will tend to 0 as t tends to infinity. As in previous case, I is something like exponential to negative alpha t, and then here we have I, and then cosine of omega d, omega prime t plus phi, something like this. Okay, so when t is very large, then this term will vanish. So the only thing we would like to consider is only the particular solution. Of course, sometimes you may consider the complete solution, including both the complementary solution and particular solution, but it takes time. You need to write out the ODE and then go through all the steps or solve this homogeneous solution, and then solve for the particular solution, and then plug it in, and then find the initial value. But yeah, for this case, usually we usually only concern the particular solution, because this part will last forever. You know, as much as for the right hand side, we have a sinusoidal wave, which means that for the particular solution, IP will be like a cosine omega dt plus b sine omega dt. Or maybe you can write it as something like IP equals r cosine omega t plus phi, something like this. And then you plug into this equation to solve r or phi or a or b, or a and b. So in that case, you can just plug in IP of t equals something like d cosine omega dt plus e sine omega dt into the original differential equation, and then you may be able to solve for something like I don't try to go through it. If you have interest, you can try to solve it by yourself, because it will be helpful to you concerning about how to solve the constant coefficient ODE, because the step might be, the calculation inside is quite tedious. But if you can really solve it by yourself, then it means that your mathematics are quite good. Okay, actually, you can just plug it in the original ODE, and then you can be able to solve D and E out like this. EM negative omega dl minus 1 over omega dc all over r squared plus omega dl minus omega dc squared, something like this. You may be able to solve it. So which means that if you don't know anything about the phasor, then you can just take the traditional step, or you try to write the KZL for the circuit. Okay, so it may take some time to really write the correct ODE and then try to solve it. Then finally you may be able to get the correct answer. But the phasor, there are some mathematics behind. You may not be able to know it at the moment, but if you know how to use the phasor, at least, then you may be able to get the final answer quickly. You only need to do some algebraic calculation. Okay, so let's see how we can use the phasor for the sample problem. So here we can see the same circuit, and then it tells you that R is this value, CL, and then FD, EM are these values. Okay, what is the amplitude of the current phasor I? Okay, so first of all, we try to calculate the impedance Z to be R plus, because it is RLC in series. If they are not in series, then the expression will be different. So let's say R plus J omega L plus 1 over omega C. Then you can just plug in the value. So R is 200 and then plus, and then omega. This is omega rather than F. So it should be like 2 pi times 60, which is 120 pi. And then L is this one, 230 times 10 to minus third power. And then minus 1 over, this is still 120 pi, and then times C is this one, 15 times 10 to minus 6. Okay, so this number is 200 and minus J 90.13. Okay, so this is the impedance. This is the impedance. Then we can actually calculate I to be EM over Z, okay, which is actually 36.0 over 200 minus J 90.13. Okay, so these are the impedance. These are the general phasor, which can be a complex number. Then for some of the calculator, you can just press it. You don't really need to calculate by yourself. But if you need hand calculation, it is just like you multiply this one. Or actually, you don't necessarily need to rationalize it. You just need to consider the absolute value. So, for example, here we just need to calculate the amplitude, which means that we need to calculate the absolute value of I. Of course, you can just rationalize it first, just multiply by 200 plus J 90.13, and then 200 plus J 90.13. But actually, you don't really need to do so, because you can just calculate the absolute value of the numerator and also the denominator, and then divide it is okay. Which means that the absolute value of the denominator is 36, and then the absolute value of the this is the numerator. This is the numerator. This is the denominator. The absolute value of the denominator is 200 square plus 90.13 square, and then take the square root. So this is nothing but 0.1648. Okay, this is the amplitude, which means that the amplitude is nothing but so the amplitude is nothing but this one. So you don't need to write the ODE like that, and then you just need to calculate the impedance, and then you can find out the amplitude of the current quickly, and also the phase. For part B, it asks you what is the phase of the current phasor. So just now we have I to be this one, 36.0 over 200 minus J 90.13. Okay, so we need to calculate the phase. So the phi is nothing but arctangent of the imaginary part, which is negative 90.13 over the real part, which is 200. Okay, so this will be a negative number. So this is actually negative 24.3 degree. Or you can also write it as negative 0.424 radian. Okay, to convert it from degree to radian, which means that it is something like negative 24.3 degree divide by 180 degree and then times pi. Okay, so this is a high school trigonometry. Okay, so this is the phase. This is the phase of the current phasor. Okay, so next we talk about the power in alternating current circuit. Okay, so this part slightly related to the second lab report about the root mean square value. So yeah, hopefully we can cover it today because you need to submit the report this weekend. Okay, so here it says the instantaneous rate of power dissipation, which is actually P equals I square R. You think it is quite trivial, but yeah, for the phasor point of view, it is like V equals, so this is the phasor, and then equals I times Z rather than R. Okay, so all these are phasor notation. Phasor notation. But here, when we talk about the power consumption, it only related to the real part, because for the inductor and capacitor, the energy are only stored there. It just oscillate from the inductor to the capacitor, and from the capacitor back to the inductor, back and forth. The power there doesn't really consumed by the inductor or capacitor. It's just temporarily stored there. So the only element that can dissipate the power is the resistor. So here P equals I square R. Okay, so in that case, I square, I is sinusoidal, which is like I sine or cosine doesn't really matter because it's just a time shift. Okay, so I is actually something like absolute value of the phasor I, and then sine of omega dt minus phi. Okay, so in this case, we will talk about the average power, which is also known as the RMS value, which is this is related to the root mean square value, which is shown here, I over square root of 2, which or maybe I can say this is absolute value of I over square root of 2 is called the root mean square value. We can also denote it as IRMS. IRMS equals I over square root of 2, or VRMS equals V. Or maybe we don't use absolute value here. But for the phasor, we need to take the absolute value. Okay, why we need to take the divide it by square root of 2? Because we would like to concern about what is the average power consumed. When you look at this function, it is a sinusoidal with a square. Of course, it is still a sinusoidal because when you learn trigonometry, this one can be substituted into another operation. So here we see that, let's see, this is P. Okay, we draw this function here, which means that this is P equals something like I square R and then sine square of omega dt plus minus phi. Yeah, the phase doesn't really matter. Okay, so actually I think this one is just let phi equals 0 for simplicity, because what we want to do is that we try to calculate the average power within a period. Okay, this is actually one period, 一个周期. Okay, So we try to calculate the average power by, we just calculate what is the total energy in a period, and then we divide it by the time. So we have this expression. Okay, of course, we just integrate for the whole thing, but this is a constant over the period. So this is just like a factor. So when we try to calculate the average power, the P average is like integration of P dt from 0 to 2 pi, from 0 to, or maybe 0 to t, 0 to t, and then 1 over t, something like this. We just calculate the total energy within one period, and then divide it by the period. Then it will be the average power. Okay, so we just plug in this one into here. So this is a constant, so that this term will move to the front out of the integration sign. We only need to integrate this thing. Okay, so this is a sine square. So let's consider only this part. Okay, so and finally you just multiply it by I square out. So finally we will have I square out there. Okay, so this is sine square, and then when you learn trigonometry, you know sine square of x equals 1 minus cosine of 2x, and then all over 2. Okay, so we need this identity so that we can change it to 2 times omega dt minus phi, and then 1 over t. Okay, so for this integration, this 1, okay, integration of 1 dt, and then from t 0 to t is nothing but t. It's nothing but t. Okay, so this part t and t will cancel, which gives you 1/2. And then for this one, you integrate a cosine for 2 periods because of this frequency is double. So you integrate a cosine for 2 periods, so it will give you a 0. So for this part, it just gives you 0. It just gives you 0. Okay, if you don't believe, you can just try to integrate. So the cosine will become sine of 2 omega dt minus phi. And then for the chain rule, you just divide it by 2 omega d. And then you plug in t equals 0, and then t equal capital T. And then you will find that omega dt is 2 pi. Yeah, because this is period, this is the frequency. So omega dt is 2 pi. So it will be like a sine of 4 pi plus 4 pi minus 5 minus sine of negative 5. And then this one will turn out to be a 0. So the second term will be a 0. So in short, this integration is 1/2, which means that the integration of the whole thing is 1/2 of I square out. So here we have a factor of 1/2. Then we try to plug it inside the square side, which makes it like the phasor I over square root of 2, and then take the absolute value, and then we have a square. So then finally, it is like P average equals I RMS square times R. Yeah, because for DC, if I is fixed, we would like to use P equals IA square out. But if it is AC, we need something like a P average equals 1/2, and then I square out. Then it may be quite confused, or sometimes we need these two, sometimes we don't need. So in that case, for AC, we just use IRMS, which means it is the root mean square value of the current, and then take the square and then out. So it turns out to be I square out, although it has a subscript there. So in that case, we have I RMS and also V RMS, which means that P is something like I RMS. P average is like I RMS times V RMS, because originally it's like I RMS square R, and then V RMS is actually I RMS times R. Yeah, so it also matches when we have a DC source, we have P equals I times V. If we don't consider the RMS, we need a factor of 1/2. And actually in the multimeter, what you read is actually the root mean square value rather than the peak value. So when you try to calculate the value in the lab report, you need to carefully consider whether we have a factor of 2, whether we have a factor of a square root of 2. Otherwise, when you compare the value you measure and with the theory, then there may be a factor of difference. Other factor may be like the length given to you is the diameter, okay, diameter, which is not radius. Diameter is 2 times of radius. In case you forgot, okay. So the number shown on the coil is the diameter phi. This is phi. So when you try to plug in the value in, there's a formula on the lab value. It is the expression is in terms of R rather than this is R rather than phi. So you need to divide it by 2 to make it a radius. Okay, so you need to be careful, otherwise you may make things different. Okay, so it means that we have a P average equals to I RMS square times R. Okay. This is not this one. We still have a cosine phi there. We still have a cosine phi there. It should be like okay. So this here it should be like I times V over 2. Okay, so here we will have a phi factor here because we have Vt to be Em cosine of omega dt, and then also we have It to be Em over Z, and then cosine omega dt minus phi, something like this. Okay, so when we need to use IMS, our VRMS to calculate. Okay, so this term is like, this is absolute value of I, this is absolute value of V. Okay, so here when we try to calculate P average, it is like 1 over T and then integration of Vt It and then dt from 0 to T. And then we will have something like Em over Z square, Em over Em square over Z, and then times integration of cosine omega dt, and then cosine omega dt minus phi dt, and then from 0 to T. And then of course we need to divide it by T. This thing is actually absolute value of I times absolute value of V over T. Okay, and then integration this part. Okay, so when you learn trigonometry, you know, on cosine times cosine, it will be like cosine times cosine and then minus sine times sine, something like this. So you need to know, you will have you will have something like cosine, maybe I'll just write here, cosine A cosine B will be like cosine A plus B and then plus cosine A minus B, and then here we have a 2 here. So 2 cosine A cosine B equals cosine A plus B plus cosine A minus B. So if you try to just add these two together, you will have 2 times of omega dt and then plus minus phi. You integrate it to be a 0. And then if you have negative part, so this one minus this one, it turns out to be cosine of phi. To be cosine of phi. And then of course, you still have a 1/2 factor. So finally, it turns out to be 2 and then cosine of phi. And then we just still have a t here. So multiply by t. So this t and t cancel. Finally, this 2 term becomes I RMS and V RMS. You just split these two into 2 square root of 2. So absolute value of I over the square root of 2 will become I RMS, and then this one over square root of 2 will become V RMS. And then finally, you have a cosine of phi, which means that this power average related to the phase difference between the voltage and the current. Yeah, if they are in phase, then all the power will be consumed. But if they are with a 90-degree phase shift, then there will be no power consumed. All the power will be oscillating between the L and C. No power is consumed. Okay, so yeah, but this is actually something more hardcore related to the power stuff. Okay, but yeah, so let's have a 10 minutes break first. And